Okay, so today we're going to discuss the first part of chapter 10. I'm just going to cover 10.1 today, especially since you guys have your exam on Thursday. So that way on next Tuesday, I'll finish all of chapter 10. And chapter 10 is more kind of theoretical, so it's not as like math intensive. So I feel like we should be able to get through this whole chapter pretty quickly, which is why another reason I kind of want to save a lot of it till later, so you guys will remember for their next exam. Okay, all right. So I'm just gonna go through the changes of state and kind of what that means today. Okay, all right. So changes of state. So, changes of state. How do the properties of liquids, solids, and solids differ? And what happens when substances undergo a change of state? So, we've briefly talked about this, right? And like in the beginning of class, we said that there's three changes or three state physical changes, right, that happen and goes solid, liquid, and gases, right? So every time, and aqueous is the other area, but that's not a phase change, right? Those are just different states that we can have our substances in, right? And so the physical changes, there's no chemical process that has that the compound has undergone, right? So it's just going from, like, when you think of water, ice is a great example, or just water is a great example, because it has three different phase changes, but the actual chemicals did not change, right? Just the physical aspects. So if we like think about water, we can think about it in three different phases, right? We have solid, liquid, and gas. So remember this triangle here, right? The phase change triangle, right? Where you're going to have different words that are going to represent the different changes of the states. So if you were to talk about from solid to liquid, right? What do we have? We go from solid to liquid. What happens when you have a piece of ice and it goes into a liquid? It's called melting, right? So the ice melted into a liquid. Well, if you do the reverse where you have a liquid into a solid, well, what happens when you put ice or water into the ice trays and put it in the freezer? It becomes a solid, right? So that is freezing. So those are one phase change. And then the liquid into gas. So when you have liquid, right? So let's say if you have a boiling, or you want to boil water, and you have your regular pot of water, you fill your pot of water, or your pot with water, right? You put it on the stove. So now I start boiling the water. So now what's happening? My liquid is becoming a what? A gas, right? So that process is called vaporization. So the process, the state change going from a liquid to a gas is called vaporization. So when something is vaporized, right? So whenever somebody says something like that, this substance has been vaporized, right? Vaporization just means evaporation. It's another word for evaporation, which really means the state change from a liquid to a gas. So anytime that you're cooking, boiling water, that's a vaporization change. That's kind of the way you want to think of it, right? It's vaporized. And then going from a gas to liquid, so let's say you have a top on top of that pot, right? So you have your regular water, you're boiling that water. That water, right, is boiling, and then goes from water into a steam, into a gas. Now, if you had a top on that pot, right, what happens to that gas? Well, it goes to the top of the actual pot, right? It sits on the top, and then what happens? When you pull off the top of your pot after you've been boiling and all that steam, right? What happens under the top? It becomes a liquid, right? You see that there's like these water droplets, because that's going from the gas to liquid, which is condensation, right? So going from that steam that rose from that vaporization process that happened from the liquid to the gas, right? After that gas is formed, it goes back to liquid through the condensation process. And the last phase transition is gas to a solid. So you want to think of gas to a solid is a deposition. So I kind of think about it like, so you have all these kind of gas particles that are like depositing into this structure, into this area to create a one solid. So I think of all these gas deposits into the structure, into the solid structure. So like when I think of deposition, so the phase change of deposition is going from a gas to a solid. It's like all these gas particles depositing into a solid. It's just a way to think about it. And then the opposite is going to be sublimation, where you have a solid into a gas. So I just think of solid, it starts with an S, sublimation, so solid into a gas. Okay, so just a quick little review of kind of all those different state changes. So now we're going to go into that a little bit more detailed. So we have liquid to gas equilibrium, right? So we have a state in which opposing processes occur at equal rates. So liquid to gas, you have going liquid to gas is evaporation, and then gas to liquid is condensation. And remember, I gave that example of when you're boiling water and you have a top on top of the pot, right? So when you are boiling that water into a gas, that's called vaporization, or AKA evaporation. So when you're boiling water to the gas, it's evaporating, and then the gas going back to a liquid is condensing. So the gas, that's another way to kind of think about it, that the gas, right, molecules are kind of all over the place, right? We know gas molecules move around really quickly, so they're moving around, and in order for the gas to go to a liquid, kind of think about it like these actual molecules have to condense together to create the more structured structure of a liquid. So when you think of evaporates, you want to think of that liquid as leaving, it's vaporizing, it's evaporating right into a gas, into all these particles. And then the condensation is when it's condensing back into a liquid. So in the above equilibrium, the rates of evaporation and condensation are equal. So what this is basically saying is that this process of the liquid turning into a steam or a gas, and then that gas going into a liquid, that process is going to happen at the same rate, right? So you kind of want to think about it in the sense of if you have like a freezing point and a melting point, right? So that at that rate, at some point, this water is going to be boiling, and at some point, the water is going to go be condensing, right? And so the rate at which those happen is going to be equal. It's not going to be that there's going to be a higher rate to get it from a liquid to a gas. The rate from a liquid going to a liquid to a gas is going to be higher than the rate of it going from a gas to a liquid, right? There's not going to be one that's going to be a faster rate than the other. They're going to happen at the same time. So as quickly as this liquid goes into a gas is just as quickly as the gas going into a liquid. Hopefully that makes sense, right? So this equation is the same, happens at the same speed as this equation. Okay, hopefully that makes sense. Okay, so boiling point. So boiling point, the temperature at which boiling occurs. Boiling point. At what point that the temperature at which something boils. So the gas produced by evaporation exerts a pressure on the liquid below it. At an equilibrium, it is called vapor pressure. Boiling occurs when the vapor pressure equals the external pressure of an atmosphere. Normal boiling point occurs when the atmospheric pressure is exactly 1 atm. So, just to touch on, let's start at the beginning. So, when this says the gas produced by evaporation, so evaporation, what is the phase change of evaporation? Well, we just talked about evaporation or vaporization and condensation, right? So if something is condensing, what is it doing? Those gas molecules are condensing to make a liquid. So they're coming together, right? To make a liquid, to make a more structured structure, right? And the evaporation is doing what? It's separating, it's evaporating, right? So that's going from a liquid to a gas. So the gas produced by evaporation exerts a pressure on the liquid below, and this is called below, and this is at an equilibrium called vapor pressure. So when this evaporation is taking place, these gas molecules are leaving this liquid phase, right? What the actual molecules are going to be exerting a pressure on the liquid. So remember when we were talking about gases and we talked about the concept of pressure, right? So the concept of pressure for these gases is from what? Is from them colliding with other things, right? So if we were talking about a balloon, so in a balloon, these helium molecules, the pressure that each molecule or that's going to be in this balloon is going to exert is going to be based off of its collisions, right? So based off of how much pressure it's exerting to other like atoms that it's colliding with as well as its surroundings. So how much is bumping into the wall or bumping into another molecule. So every time it's bumping into the wall, it's exerting pressure, right? Because like when you bump, it's like pressure. So it's pressure. So that's what you want to think of these molecules as like pushing. It's like pressure. They're just floating around and exerting pressure wherever they're floating around. So in that sense, this gas that's evaporating, right? So now I'm a liquid, and now I've kind of evaporated into these little gas molecules. And so what am I doing when I'm a gas molecule? I'm moving around, right? I'm exerting pressure. So now what is the area that I'm going to be exerting pressure on? The liquid that's below me. So I'm not fully a gas yet, right? I'm in the transition to a gas. I'm in that boiling phase. So in that boiling phase, you almost kind of want to think of it kind of like a domino effect in a way, right? So once I get to the boiling point, then there's going to be a time period where there's a plateau where there's no temperature change, and I'm slowly going from a state of liquid into gas. I'm slowly going into that boiling phase. Right? So I'm going from this liquid into a gas, and the temperature is not changing. So it's kind of like, okay, I started boiling and now I'm boiling, and then it'll kind of go higher into whatever next phase is happening. But so in that, right? So as I'm like boiling, right? So these these molecules are changing from liquid to gas. So as that's happening, there's all this pressure from those gas molecules that is basically coming in contact with the liquid that it's forming from. I hope if that makes sense. So it's like these new gas molecules with still some liquid on there. And so that pressure that those new gas molecules are creating against that liquid is what we call vapor pressure. So when you hear vapor pressure, you want to just think of in that phase change, the pressure that's being exerted from those gas molecules to the liquid. Okay, so in that phase change of evaporation, the vapor pressure is from the actual gas molecules that are being created to the liquid that it's coming from, in a sense. Hopefully that makes sense, okay? So it's like the pressure from the vapor, right? Because it's called vaporization. So the pressure is from the vapor that's being created. Yeah, right? Okay. So boiling occurs when the vapor pressure equals the external pressure of the atmosphere. So we have, like as we said, right, there's atmospheric pressure. So that's something that can be measured, right? So as we're sitting in our places, because that's where we all should be right now, right? So as we're in our houses or wherever we are, there's a certain amount of external gas, right? There's gas all around us. And so what is that gas doing? It's colliding, right, with either itself, other molecules, or just other compounds, right? And we could be one of those compounds. So it's creating pressure by just having collisions. So the same would be true when you're, for instance, boiling water. So when you have your pot of water, right, you don't have a top. You just have your water, you're turning on the heat, right? And that water begins to boil. Basically, what is happening is that you're increasing this temperature to create this phase change, right? And so the boiling point, the actual physical boiling that you see, is from the external pressure. So all those gas molecules that are just normally in the world and in the air are actually colliding with that top of that water. So that water that's in your pot, there's these external gas molecules that are like colliding with the top of your water, right? Because these gas molecules are everywhere. So it's colliding with anything that's around us. So in this pot of water, it's colliding with this top of pot of water. So, but what are we doing? We're creating a pressure ourselves, right? By increasing the temperature, we're therefore changing the phase of this molecule, right? We're changing the phase from a liquid to a gas. So in doing so, we've created our own vapor pressure, right? Because as we are going to, as the liquid becomes a gas, there's going to be these molecules that are going to be pressing down, right, on this liquid. So there's already a little bit of pressure, right? There's already some pressure that's happening within this phase change. But now you're going to be adding this external pressure onto that vapor pressure. So you almost want to think about it like, let's say if this is your water, right? This little here, I'll use this. This is my water, okay? And let's say if from here to here, the boiling water is happening, right? And I start seeing some bubbles happening. I turned up the temperature, I start seeing some bubbles happening, right? A little bit of mist, and now there's bubbles. So basically what's happening is when you see that mist happening, right? That gas phase changing, the reason it starts boiling is that there's an equal pressure between the external air and the pressure that's happening from the phase change from the liquid to the gas. So this is starting to create a phase change and create pressure. So there's like pressure. It's like a little pressure cooker. Pressure, 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 pressure. And then there's also the environmental pressure. So this pressure is here. So now you have these two different pressures that are colliding. So you have the pressure from the glass or from your pot, from the liquid, and then you have the external pressure. So these two combine and they hit each other, and that creates this boiling effect. Kind of cool, right? So you have the pressure that's happening within itself from the state or from the actual phase change, and then just the external, and then that's where boiling actually happens. So that's how something boils. Pretty cool. At least I think so. Actually, I'll have some water. Okay, so normal boiling point occurs when atmospheric pressure is exactly 1 atm. So remember how we talked about last time when we talked about gases, and I discussed that there's a STP, and I'm not sure if you remember, but STP means standard temperature and pressure. So when you're thinking of standard temperature, the temperature is going to be at 0 degrees Celsius, and standard pressure is at 1 atm. So generally, when you're thinking at standard temperature and pressure, that's going to kind of be that's where normally boiling occurs, and that's why it's at 1 atm, is because this would be considered like at standard temperature and pressure. the normal boiling is 1 atm because it's standard. Yeah. Okay. Okay. So liquid solid equilibrium. Okay. So liquid to solid. So the phase change for that, right, is the solid going to liquid, which means it's melting, or the liquid going to solid, which is freezing. So this is a pretty basic equilibrium that we know already, right? So freezing point, FP. So these are going to be important I guess units or abbreviations to know. Okay, so because you're gonna when we'll be writing possible problems, it'll say freezing point or melting point. So note that FP and like FP is freezing point and MP is melting point. So freezing point, the temperature at which the freezing of a liquid into a solid state occurs, right? Which basically kind of makes sense. So at what rate at the state of which this liquid turns into a solid. So at that point, it's called the freezing point when it freezes, and the melting point is kind of the opposite, right? This occurs at the same temperature as a freezing point. So the equilibrium just kind of is that like last time, right? So what it's basically saying is that each one of these are going to be changing at the same rate. So the same speed at which this liquid is going to become a solid is going to be equal to the same speed at which the solid becomes a liquid. Okay? So hopefully that makes sense. Okay, so let's go into this heating curve. So this kind of gives you more of a visual aspect as to what we're talking about. Okay, so heating curve shows the phase changes of a substance in a graph plotting temperature versus heat added at a constant pressure. Okay, so when we are looking at this, graph here, so we have temperature and heat added. So this is obviously, like, let's say this is 0 and this is 300. I don't know, just creating that, right? So this is the temperature. I'll just so this is like 0 degrees. Okay. So that's the 0 degrees there. And then we're going to add heat. So this is like, let's think about this as your Bunsen burner, okay? So you're adding consistent heat this whole time. And this is kind of what happens as you're adding more heat. Because as you're adding more heat, right, what's happening to temperature is increasing. Because if you think about when we do our experiments and we're taking the temperature, right, we add constant heat as the temperature rises. And the temperature begins to rise, right? So when you're looking at the heat changing curve. So this top portion, right, is talking about how you're going to be melting and then evaporation. And then this is the changing, the opposite, right, going from that evaporation, the condensation, and into the freezing. So the phase changes, it shows you kind of what happens as you're increasing the temperature and adding more heat. So when you are at 0 degrees, like, so let's think about this as a physical sense in terms of a piece of ice, right? So if you have a piece of ice, so this is where your ice is. This is your ice cube, right? So now you're adding heat to your ice cube, so now the temperature is increasing, right? You're adding more heat. Now that ice cube is going from the state of being an ice cube into liquid water, okay? So that's what you want to look at, and that's kind of what I was talking about earlier, is that as you're going from this point of a liquid from a solid to a liquid, this is going to be increasing, right? So you have to add more heat until you get to that point. So once you get to that point, that's where there's going to be this melting and freezing happening, right? So you're adding more heat onto this piece of ice. You're adding more heat, you're adding more heat, you're adding more heat, right? And at this point, now there's going to be, you added so much heat that if you left it at that temperature, right? So this is not to say to decrease, you're not decreasing the temperature, but if you left it at that same temperature, this ice will melt from full ice into all liquid, right? So once you get it to the point where it begins to melt, if you leave it at that same temperature, you're not going to, there's no more increase in temperature, right? The temperature is not going to increase until it's reached its final phase of melting, if that makes sense. So you're starting with this piece of ice, you're adding heat, the temperature's going up, the temperature's going up. Boom, it gets to a point of when it's begun to melt, right? Now, there's no more temperature increase. You're keeping the heat the same, right? But because we're in the phase change, there's actually no increase in temperature. And so while it's actually in the state of changing from a solid to a liquid, no temperature change is happening. It's just kind of like once you've gotten to that plateau, once you've got to the point of the temperature that you need it to get to so that it can melt, then it'll melt, right? Does that make sense? So you have to get it all the way up to the turn temperature of when it begins to melt. And then once it begins to melt, there's no more added temperature that's needed for it to melt, right? Because you already got it to the temperature that it needed to get to melt. So once it's at that temperature, it just needs to be at that temperature to continue to melt. So then, now it's fully melted, okay? So now, what's the next phase? So let's think about this if you put some ice in a pot. So first you melted this ice. The ice went from a solid ice to liquid water, right? So let's say that's where we are now. So now we have our liquid water. So now we want to boil this water, right? So now we're going to add more heat, and as we're adding more heat, the temperature is going to go up. So we're boiling our water now. So we're adding more heat, temperature's going up, water's boiling, or getting warmer, not boiling it. It's getting warmer. So it's still water, and this is kind of that phase, right, where you turn on, when you pour a pot of water that you want to boil, and you put it on the stove, right? And it's just sitting there until all of a sudden you kind of start seeing it boil, right? So do you want to think about this time is that time period that you have to wait for the water to boil. So you are here and it's melted, right? But now you want to heat it up even more so it can begin to boil. So it's a piece of ice, and now it's a still piece of ice, still piece of ice, still piece of ice. Boom, here. It's now starting to melt into a liquid. Now it's turning into a liquid. Now it's a liquid. Now it's still a liquid, and it's getting warmer, and it's getting warmer, it's getting warmer, it's getting warmer. Boom, here. Now it's going to begin to boil and turn into a gas. Okay? So hopefully that kind of makes sense. Okay, and so that's the evaporation, right? So these plateau parts are saying that you don't need the temperature doesn't increase as it's going through that phase change, right? Because it doesn't need, in order to go from here to here, you just needed it to get to a point of breaking kind of those bonds so it can begin to change states. But you don't need any more temperature. The temperature doesn't increase while it's changing the state. But to go from this state change to this state change, you're going to have to increase the temperature. So, and then the same is true in the opposite direction. So if we had that top on that pot, right, and we evaporated or vaporized our water, and now that water is collecting on the top of the pot, and like I was saying, right, that water, that gas is condensing now into like a liquid. So now, right, let's say if I take the heat away, right, because this thing, I'm adding heat. So that means I'm looking at this forward one. So if I'm adding heat, then I'm going to be melting into evaporation. And then if I took away the heat, then I'd be going into freezing. So when I'm condensing, right, so let's say now this evaporation became all gas. And now the gas is slowly is gas, and now it's still gas, 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 but you're taking the heat away. Taking the heat away, taking the heat away, still gas, still gas. Then all of a sudden, there's that change from gas into a liquid, right? So that's a certain temperature. So at a certain temperature, it changed from a gas to a liquid. And then that's at the same temperature. And now it's all liquid. And now you want it to go so now, because you have your gas and liquid, and now you're going to go from your liquid into your solid, right? So then you have your liquid, and it's still liquid, it's just getting colder, it's getting colder, it's getting colder, and now from here it's going from a liquid to a solid, right? And so then the liquid to a solid, which is freezing, and then it's just getting colder and colder and staying into the solid area. Okay, so hopefully that phase transition makes sense. So they have another example looking at the cooling curve. So this is kind of exactly what I was just showing, but the opposite. So you have two curves. You have your heating curve, right? And know for these curves which phase changes are related to which curves. So for instance, for the cooling curve, you're going to be looking at condensation and freezing, right? Because you're cooling this substance, and which means you're going to be going in like a negative or opposite direction. So here, if with evaporation, right, you're adding more heat. It's going from liquid to a gas. So here now, if this graph is saying we're removing heat in this direction, so if I'm a gas here, I'm a gas. Now I'm removing the heat. I'm gas up until this point. That's a specific temperature, and then I'm going to go from a gas into a liquid, and that's going to be condensing, right? And it's the same temperature. There's no heat. There's no temperature change. So now that I'm a liquid, I'm going to be getting colder and colder and colder and colder and colder until I get to a specific point that's going to be a specific temperature that's going to help me change into a solid. So then I'm going from a liquid into a solid here, which is freezing. And then I'm getting colder and colder and colder and staying in a solid. So this is the direction for cooling, and then this is the direction. Okay, oops. Okay, hopefully you can see this. Yes, okay, so this is the direction. This bottom one is the direction for cooling, so make sure to write that down. This is the direction, and then the heating is, you want to think of this top part is the direction, okay, for the heating curve. So the melting to evaporation is for heating, and then condensation to freezing is for the cooling, okay? All right, so the last part of today. So these energy changes that are taking place, right? So energy changes within the phase. Within the same phase, the change in energy is accompanied by the temperature change, where Q is the heat, M is mass, delta T is the change in temperature, which is T final minus T initial. So really important to remember that it's the final temperature minus the initial, okay? And C is the specific heat, which is, what is specific heat? The amount of heat that must be added to 1 gram of a substance to raise its temperature by 1 degree Celsius. So we've actually discussed this before, right? So when you think of specific heat, so this is a value, first of all, that you aren't going to have to know. It's always going to be given to you, so don't worry about that. So, but the concept of specific heat is saying how much heat do I need to add to increase this substance by 1 degree. So if I have 1 gram of this, for like 1 gram of this substance, how much heat do I have to add to it to raise its temperature by 1 degree? So that value is C. So for instance, with water, right, the C is 4.18 joules per grams degree Celsius. Okay, so this is saying, remember, joules is for the energy, and then grams is weight and like temperature. So when we think of the specific heat, so this is how much energy is needed to increase 1 gram. So if you have, like, let's say this is water and this is 1 gram of H2O. So if I want to have raised this, and this, let's say this is at 30 degrees Celsius. And if I want to raise how much heat do I need to add to this gram? How much heat? How much heat? Right, I want to add heat to this. So how much heat do I need to add to this water to get the temperature to go from 30 to 31 degrees Celsius? So that heat is 4.18 joules per gram degree Celsius. So that's how much heat I needed to make this 1 gram of that was at 30 degrees Celsius to go to 1 degree Celsius. Okay, so hopefully that makes sense. So that is your specific heat. So that's how much, it's the specific heat that's needed for every 1 gram to go to 1 degree Celsius. So this equation you do need to memorize. You do need to know that. You don't need to know the delta C, or the C, because that will be given, but you need to know what the Q is and figure out the M and figure out how to calculate the T. Okay. So, and the concept that we're talking about is the energy changes that are within these phases. So every time that there's a phase change, right, there's a certain amount of energy that's needed, and so this is how to calculate that. Okay, so energy changes during phase change. Each change of state takes place at constant temperature. So remember how I was saying that as the state is actually changing, there's no change in the temperature, right? So once you get to, so water boils at 100 degrees Celsius. So it doesn't boil past 100 degrees. That's not the boiling point, right? If it's 101, it's past the boiling point. The boiling point is 100 degrees. So at 100 degrees, water is boiling, right? So it doesn't need to go past 100 degrees to boil. So that's kind of what that means. It's a constant temperature. At this constant temperature, there's going to be a phase change. So each change takes place at a constant temperature. Any phase change is accompanied by energy change. So if there's a change in state, right, there's going to be a change in energy. And so that is Q equals N, which is in moles, times the heat of the phase change. So, molar heat of fusion. So, energy required to melt 1 mole of a substance. So, this is something that you need to know, but we're not going to be necessarily using this equation. Just FYI, we are going to be using the equation, the previous equation of Q equals M times C times delta T. Okay. but this is just good for you to understand in terms of the energy in terms of phase changes. So molar heat of fusion. So fusion, you want to think of is how much is it required to melt 1 mole of a substance. So it's like melting. So if I want to think of how much energy is required to go from a piece of ice to a liquid for like 1 mole of that, or mole of vaporization. So remember, vaporization is evaporation, which is that liquid going into a gas. So what is the energy required to evaporate 1 mole of the substance? So how much energy is required for 1 mole to evaporate? And the molar heat of sublimation, the energy required to sublimate 1 mole of a substance. So remember, the sublimation is the solid into a gas. So how much the molar heat that's required to go from the solid into a gas. Okay, and then we're going to end with this problem. Okay, so this is how you would use that information that we were just talking about practically. So, calculate the heat absorbed when 125 grams of water at 72 degrees Celsius is converted to steam at 186.4 degrees Celsius. The specific heat of water is 4.18 joules per gram degrees Celsius. The heat of vaporization of water is 4.0 times 10 to the fourth, and the specific heat of steam is 2.02 joules per gram degrees Celsius. Okay, so there's a lot that is said in here, right? But what do? The first thing that we want to make sure that we always write down is what? Our given. And then what do we want? So then we can see, like, we can pull out the key information that we need in order to solve this problem. So what are we given? Okay, we're given, wait, what do we want? Okay, well, first it actually tells us what we want, right? That's the first thing it says. It says calculate the heat absorbed. So we're going to go back to this problem, right? So when we're talking about the change in energy, we want to use, when we're talking about the heat, right, we're trying to understand from this phase change, what was the heat that was, used, right, in this phase change. So we're going to be using this equation. So, let's see. So the equation we're going to be using is Q equals MC delta T. Okay, MCAT. So you're going to be using MCAT, kind of. It's not an A, but it's a delta. So Q equals MCAT. And that's how we're going to calculate how much heat was absorbed, right? Because, and it says absorbed, obviously, because we increased in temperature, right? We went from 72 degrees Celsius to 1 degree Celsius. So now when we're looking at this graph, that's also something that I would want you to know is what phase change is going from D to E, right? So what is happening? If we're adding heat, okay, so that means if we're adding heat and looking at this graph, what kind of graph would this be? This would be called a heating curve. Right? It's a heating curve because we're adding heat. So if this is a heating curve, then that means that we're going to be heating our substance. So if we're starting at 0, right, then you want to think that 0 is always going to be your ice, right? Okay, so we're at 0. So then if I'm adding heat to my ice, what's happening? I'm going to be melting, right? Because I'm going from ice to liquid. And that's what's happening. Remember how anytime you have the plateau, that means it's a phase change, because at this point, this temperature is what's the important part that you need for it to melt. So at this temperature, it melts, and then you add more heat. And then what happens? Once the water has melted, what phase does it go through? So you have your ice, you put your ice in your pot, the ice is now a liquid, water liquid. Right now your pot is still on the eye, adding more heat. And so what starts to happen to that water? That water begins to warm up, right? And then what happens as the water reaches, what's the next point that it reaches? What happens to the water next? It boils, right? So and that's from the equaling of the vapor pressure and the external pressure, right? That's where the boiling comes from. And what happens when what phase change happens when it's boiling, when it's going from a liquid into a gas? Vaporization, right? Or evaporation. Okay. So vaporization or evaporation, right? Because that's where we're going from D to E, is vaporization or evaporation. So that's going from the liquid to the gas. Okay, so I just wanted to point that out so you understand what you're seeing on this chart. So when this is saying that it absorbed heat, right, you can see here, well, it absorbed heat in the phase of going from a liquid to a gas, or not that phase, but going to the point of switching phases of being from a liquid to a gas. It was at 72 degrees, and then it ended at 186.4. So it started here at a liquid here, and then it went to a steam. And so it absorbed heat because it's on the heating curve, so it added heat in order to do so. So when we look at our given, our M is going to be our mass, which is 125 degrees, 125 grams. Okay? And then our temperature of water at 72 degrees is converted to steam at 186.4 degrees Celsius. So the change in temperature is T final minus T initial, which is equal to delta T equal to 186.4 degrees Celsius minus 72 degrees Celsius. And that is 114.4 degrees Celsius equals delta T, right? And now, what's the last part of information that we need? So we have our mass, we have our delta T, right? And now we need our specific heat. So here they give us all this information, right? They say they give us the specific heat, they give us the heat of vaporization, they give us the specific heat of the steam, right? So when we're doing these problems, it's like you want to think to yourself, well, we have to pick a specific heat, right? And that's what C is. So when you're looking at this, really all of this is here, not to necessarily, I guess, confuse you, but for you to see that you have to make sure that you know what C is, okay? So C is the specific heat. So just looking at these three, so you have the specific heat of water, heat of vaporization, and specific heat of steam. So we can just say automatically, we know we don't need the heat of vaporization, right? Because it's literally not what we have in our problem. We need our specific heat, so we don't need the heat of vaporization. So now what we want is we want to choose between the specific heat of water and the specific heat of steam. Okay, so the specific heat of water is what we're starting with. So when we're going from these changes, you want to say, well, which state did we start in? So whatever state that you started in is the specific heat that you're going to take. So we start as water and we convert to steam. So we're going to use the specific heat of water versus specific heat of steam. So the specific heat of water is going to be 4.18 joules per grams degrees Celsius. Okay? And so now you're just going to go ahead and plug all of this in to your equation. So my equation is Q equals 125 grams times my specific heat, which is 4.18 joules per grams degrees Celsius. And that's all times my 114.4 degrees Celsius. That equals, I'm going to erase this problem, this here. And that whole thing equals 59774, or 6.0 times 10 to the 4th joules. Either answer is fine. No need to put it in scientific notation unless I, specifically ask for that. Okay. Yeah. So, and then you can see when you're looking at this, you can actually see that some of the units cancel out, right? So that's also the other thing that's nice about the specific heat. If you didn't remember the units, it tells you what the units are, because we have our grams and our degrees Celsius, right, under our joules. So that's how you're able to cancel out this grams here and then this degrees Celsius here. And then you're just left with joules. Okay, and so this is the final answer for Q. So that's how much heat was absorbed in transitioning from here to here. Okay, so that's like here. That's like how much heat was absorbed here. Alrighty. Okay. So, yeah. So that is it for now, and I will see you guys in a few. Alrighty. Toodaloo.